Okay, so Java gives us two classes, ArrayList and LinkedList. They have the same methods and they yield the same results. Why did Java give us two? Well, we mentioned that because of performance reasons. So I need to take a little aside and talk in a very computer sciencey way about ArrayList versus LinkedList performance. But the good news is if you don't understand this, it doesn't really matter if your lists are small. If you only have 1,000 elements, it doesn't matter very much if you use ArrayList or LinkedList. Also, if you have the actual data, just try it both ways and time it. But often you have large sets of data and your data can change. And you would like to know, how will my performance change if I switch from ArrayList to LinkedList or from LinkedList to ArrayList? If ArrayList was always better, they would just give you ArrayList. If LinkedList were always better, they would just give you LinkedList. But ArrayList is good for certain operations. LinkedList is good for other operations. So let's talk about it. So a linked list, you have your top level variable, and it points at a little data structure. And inside this data structure, you have a linked list of pointers where you basically have a box pointing at another box, pointing at another box, and so forth. And the data structure points at the first box, and it points at the last box. And then let's ask a question. How long does it take to insert a new element at the beginning? Well, you just go in here, you make a new box, you attach the pointer to here, and you move this little pointer there, and you're done. And how long that took was independent of how many little boxes you have down here. So in computer science, the way to say that is big O1. The performance is the same regardless of how big it is. In other words, inserting at the beginning of a 5-element linked list, inserting at the beginning of a 5 million element linked list takes the same amount of time. All right, well, what about an array list? Well, to answer that question, we need to know how array lists work. So you have your top level variable. It points at the array list data structure, and the array list data structure points at an array. Well, arrays can't stretch, but the array list data structure manages it. So let's say for the sake of argument it just starts with 2. It really starts with more than that, but let's say it starts with 2. And you come along and you say, well, I want to add an A into my array list. So it puts the A into the array that's managed internally by the array list. And then you say, I want to put in a B. So it puts in a B. And then you say, I want to put in a C. Well, there's no space. So internally, the programmer doesn't see this array, it just sees the top level data structure. Internally, the array list allocates another array that's twice as big. And it copies the A down to here, and the B down to here, and then it sticks the C in. And then you say, I want to add in a D, so it just sticks in a D. And then you say, I want to add in an E. So it allocates an array that's twice as big. It copies the A, it copies the B, it copies the C, it copies the D. And then it puts in the E, and so forth. Now, this argument is a little oversimplified because it doesn't really start with such a small array internally. It starts with something larger, but the argument still holds. And so the point is that an array list is internally is an array with copying. So how long does it take to insert something at the beginning? Well, you can't just add something at the beginning of an array. Arrays are contiguous chunks of memory. So what do? You have to shuffle everything down. So if you insert something at the beginning of an array list, the performance is big O of n. It's directly proportional to the size of the list. What that means is if you have a 5-element array list and a 5 million element array list, it takes 1,000,000 times longer to insert something at the beginning of the big one than it does at the small one. So with inserting at the beginning, array list is bad, linked list is good. All right, let's ask another question. You've got a list, an array list or a linked list, and you've put a whole bunch of stuff in it. And now you want to say, what's the middle element? What's the value of the middle element? How long does that take? Well, if you've got a linked list, you have to go to the first one, you go to the second one, you go to the third one, you go to the fourth one, you go to the fifth one, you go to the sixth one, and you keep counting until you get to the middle. And so the bigger the list, the more things you have to follow. And so accessing the middle element of a linked list takes time proportional to the size of the list. Another way of saying that is if you make the linked list twice as big, accessing the middle element takes twice as long because you have twice as many little boxes to follow. Well, what about an array list? Well, with an array list, internally it has an array. So Java goes to the main data structure. The main data structure looks at the array. Arrays are contiguous chunks of memory. Accessing the first element, the second element, the middle element, the last element all take the same amount of time because you just do a mathematical calculation to compute where the middle element is. So accessing the middle element takes constant time for an array list, but linear time for a linked list. So for accessing the middle element, a linked list is bad and an array list is good. Now, I do want to point out, if you loop down, the looping constructs are smart enough that they don't start over each time. So if you walk down the entire list and do something to each element, they both work fine because the looping constructs are smart enough with linked lists not to start over at the beginning each time. It remembers where you were. But if you're just looking things up, it's fast with an array list, it's slow with a linked list. Now, what about doing an insertion? Well, and you want to insert at the end instead of at the beginning. With a linked list, the answer is obvious. It maintains a tail pointer, so you can jump directly to the end. You can make one more box, attach it, and just move this pointer. And so it didn't matter how many things were here first. It could do that directly. And so inserting at the end of a linked list takes time independent of the size of the list. It's just as fast with a small list as with a short list. But with an array list, sometimes it's fast and sometimes it's slow, depending on whether there's space in the little internal array. So it takes constant time if there's space. It takes linear time if not. Because if there's no space, you have to copy everything down. That's confusing. So how much does it take on average after you do a whole bunch of inserts? And this is a very confusing question, and this is a very computer science-y answer to the question. So if you don't understand this, is okay, you can kind of take this on faith. But the basic point is that you're copying less and less frequently. And so if you look at the number of copies it had to do, let's say you started with one box, you copied one element here, you copied 2 elements here, you copied 4 elements here, you copied 8 elements there, and 16 and 32 and so forth. And if you did k insertions and you want to know how many wasted copies you did, well, 8 plus 4 plus 2 plus 1 is 8 times 2 minus 1. And so that whole thing is 2k minus 1, which means it grows proportionally to k. Now, that's a long, complicated way of saying that this copying doesn't hurt you on average. The average, or the amortized cost, is still order 1. So this is a tie. If you're inserting at the end, it doesn't matter whether you use an array list or a linked list. But if you're inserting at the beginning, you better use a linked list and not use an array list. If you build a big giant list, and then you're jumping into the middle, you say grab the middle element, grab the one that's 20% down, grab the one that's 90% down, then you better use an array list and not a linked list. Complicated, but the good news is twofold that I said at the beginning. One, if your lists are small, it doesn't really matter. And secondly, if you have very representative data, just try it both ways and time it and see the difference. That's why you declare your variable of type list, not of array list or linked list, so you can change your mind later.